So, how do we decide if some new idea is a real breakthrough or just a fluke? I mean, how does a scientist prove a new drug actually works or that a new technology is better? Well, it all comes down to this really powerful, logical way of thinking for weighing evidence against a claim. All right, let's dive into this with a pretty simple story, but one that really unpacks a huge statistical idea. So, picture this. We've got an inventor, a brand new engine, and a very, very bold claim. The big question is, right, how do we actually test it? So this whole thing kicks off, like so many great stories do, with a claim. You have an inventor who's absolutely convinced they've made something better than what's already out there. Okay, so here's the claim, and it's super specific, which is important. The new engine, they say, can run for more than 300 minutes on a single gallon of gas. Now, the current best-in-class, the leading brand, runs for exactly 300 minutes. That's our baseline, our status quo. So the inventor is saying their engine is better. But, just saying it isn't enough. You've got to prove it. Okay, so before we even get our hands dirty, before we look at a single piece of data, we have to frame the problem. And the way we do this is by setting up two competing ideas, basically two possible versions of reality. So this first idea, it's got a fancy name, the null hypothesis. But honestly, just think of it as the innocent until proven guilty principle, like in a courtroom. We start off by assuming that nothing has changed. We're skeptical. We assume the inventor's new engine is no different, no better than the old one, unless we see some truly overwhelming evidence that says otherwise. So, here's the showdown. You've got these two competing realities. In one corner, you have the null hypothesis, the status quo, which says the new engine is basically the same, and any little difference we might see is just random noise, right? And in the other corner, you've got the alternative hypothesis, which is the inventor's exciting claim, the engine really is better. And this right here, this is the absolute heart of hypothesis testing. Look, the responsibility isn't on us to defend the way things are. No. The burden of proof is squarely on the inventor. They're the ones who have to bring the receipts, the convincing evidence, to overturn that status quo. All right, let's get to the fun part, the investigation. It's time to gather that evidence. And obviously, we can't just test one engine. That wouldn't prove anything. We need to run a proper experiment with a decent sample. And here we go. Here's our evidence. They run a random sample of 50 new engines, and the average runtime comes out to 305 minutes. Now, okay, 305 is definitely more than 300, we can all agree on that, but is it enough more to be convincing? Or could that 5-minute difference just be a fluke? Maybe they just got a lucky batch of engines. That's the real question. To answer that question like a scientist, we calculate something called a test statistic. Now, don't worry about the math or the formula. The important thing to know is what it does. It basically boils down all of our evidence, the average we saw, how many engines we tested, how much the results varied, into one single powerful summary score. Okay, so now we have it. All our evidence distilled into a single number. This brings us to the moment of truth. It's time for the verdict. We're going to weigh this evidence against our starting assumption, against the status quo. So, this all comes down to one question. How surprising is our evidence really? Let's put it this way. If the new engine was actually no better than the old one, if that null hypothesis were totally true, how likely would it be for us to get a result of 305 minutes, or maybe even higher just by pure random luck? And that probability, that measure of surprise, has a special name. It's called the p-value. You've probably heard of it. I love this analogy. Think of it as our surprise-o-meter. A really tiny p-value means our result was super surprising if you assume there's no difference, which, suggests that assumption is probably wrong. Okay, so for our lawnmower test, after all the calculations, the p-value comes out to 11.9%. Now, what does that number actually mean? Well, it means there's an 11.9% chance of seeing an average of 305 minutes or more, even if the new engine was no better than the old one. Let's put that in perspective. An 11.9% chance, that's not crazy rare. It's roughly the same odds as rolling 2 dice and getting a 10 or higher. It happens, right? So this result, it's not quite the smoking gun we might have thought. Okay, so to make a final call, we can't just rely on our gut. We need a clear benchmark. And this is really important. Before you even run the test, scientists set a standard for what they'll consider proof. It's called the significance level, and very often it's set at 5%. So the rule is simple. For our evidence to be convincing, our p-value has to be less than that standard. And here it is, the verdict. Our evidence, with that p-value of 11.9%, is greater than our 5% standard. It didn't meet the burden of proof, so we fail to reject the null hypothesis. Now, notice that language is really specific. We're not saying the inventor is wrong, and we're definitely not proving the old engine is better. We're just saying that this particular experiment didn't give us enough evidence to overturn the status quo. So, yeah, in our little story, the inventor's claim didn't get proven this time. But this exact logical framework, this whole idea of setting up a skeptical, nothing has changed view and then demanding solid evidence to knock it down, this is used to make massive, world-changing decisions every single day.
But hold on. Any test can be wrong, right? What if we made a mistake? Well, the great thing about this framework is that it's smart. It actually accounts for the two specific ways we could have gotten the conclusion wrong.
And this just brilliantly lays out the fundamental trade-off. On one side, you have a type 1 error. Think of this as a false alarm. It's when we get all excited and announce a breakthrough that isn't actually real. On the other side, you have a type 2 error, which is a misdetection. This is where we miss out on a genuine breakthrough because our test just wasn't powerful enough to see it. And scientists are constantly trying to find the right balance between these two risks. And really, this isn't just about lawnmowers. This whole process, challenging the status quo with hard data, it is the engine of discovery. It's how we test if a new cancer drug actually saves more lives. It's how a business knows if a new ad campaign really worked. It's how astronomers check if data from a telescope supports a wild new theory about the universe. It's literally how we move from just believing something to having actual evidence for it. So when you boil it all down, this is so much more than just statistics, right? It's a powerful tool for thinking critically. It gives us all a structured way to challenge assumptions, our own and others, and to demand real evidence before we accept a new claim as true. So I'll leave you with this to chew on. What status quo idea in your world would you want to put to the test?